Hello? Oprah Winfrey? Why, yes, we are. You're in luck. We are doing line segment relationships in a circle today. Well, buckle up. Here we go. 6.3 in a nutshell. The first thing we are looking at is the lengths created between the intersection of two chords. As I look at this thing, I'm going to call this red and this is red. And then I want to look at GD, and that is orange. And then we, of course, have GF in green and GE in blue. And we see we have this relationship that if I take these segments and I multiply them and set them equal to the other ones, that we have an equality relationship. So CG times GD equals EG times GF. It's that easy. So when we look at these things, if our two chords are intersecting, we have this relationship, and we'll see why that is in a little bit. The next big thing I want to point out to you here is that we have a intersecting secant, so two lines that go through at 2 points on this thing. PL, the long red line here, and then we're going to go LM, the short orange line here for the top stuff, and then we're going to go QL here for the long green on the bottom, and we have LN for the short blue on the bottom. And that's it. PL times ML equals QL times NL. This relationship is true for our secant lines. If we have two lines which intersect tangent to a circle, so again, just touching in one point, we have that those two are the same. So these two segments are the same. So here, SR and ST are equivalent. So we could put a little one tick on those. Let's get into the details of this stuff. So the first thing we're going to take a peek at is if a line is drawn through the center of a circle perpendicular to a chord, then it bisects the chord and it bisects the arc. So I've kind of like referred to this a little bit. We talked about it the other day, but now we're going to see it sort of as a little bit more, I don't know, just drawn out here. So the first thing is we got this AB and CD perpendicular intersection, which gives us this 90-degree angle here. As we look at this, I'm trying to prove that CB and BD are congruent and that CE and ED are congruent. So I'm going to highlight them in their own colors here. So CB and then BD, and we will do CE and ED. Understanding that they're supposed to be going to this point E here, I just don't want to write over the circle stuff. So in terms of solving this, I don't want to do the entire thing for you because I don't want to take all the fun out of it, but I will give you a hint, and the hint is that all of the radii on a circle are the same. This segment is a quality radius, clearly straight, is the same as this, is the same as this, however poorly or just interpretively drawn they are. So if I wanted to do the same thing over here for AD, might be a good idea. It's my hint for you. Next one we're looking at here is if a line through the center of a circle bisects the chord other than the diameter. So the reason we say other than the diameter is because the diameter always goes through the center of the circle. So if I had a bunch of diameters like intersecting, it's not necessarily going to be perpendicular to the chord because it's just intersecting through the same point. So that's why we say other than the diameter. But then we're able to say that it's perpendicular to the chord. So again, line through the center bisects the chord, then it's perpendicular. So now here what we're saying is that we've got the circle, line O, okay, OM is the bisector of the chord. So RM and MS are the same. So that congruency there is what we want. Again, not going to solve the whole thing here for you because I don't want to take the fun out of it, but it might be helpful to talk about some radii. Just keep in mind, all my radii are the same wherever you want to go out to. here we are going to, oh boy, illustrate that same idea. So here basically we're going to use this to talk about the thing above. If I had some other point which was not the center of the circle, then these lengths are going to be different, and we end up getting different triangles. So here, this is just to help illustrate this theorem that we were just talking about before. Again, here is using the center. Here is not using the center. So these are not going to be congruent segments, but if I was using the center, then they would be. So kind of like a little hint for like an indirect proof if you wanted to go that route with it. Here we are looking at the perpendicular bisector of a chord contains the center of a circle. So now this is very, very similar to the past two we've looked at. And so the first thing we're starting out with is we have QR is perpendicular to the bisector of the chord TV. So basically we've got QR is splitting this thing into two congruent segments, and it comes through perpendicular. So it creates a 90-degree angle here. So I'm trying to prove that it contains point O, and point O is the center of the circle. So to prove that it contains the center of the circle, we can do an indirect method. So this is what we're referencing up here as our indirect method for solving this, is we can say, okay, well, what if it was not the center of the circle? Okay, so let's just say the center of the circle is somewhere else. I know, it's heresy, but we're saying, okay, well, imagine we have some other point which is not the center of the circle, but we're going to call it the center of the circle. So as we look at this thing, basically we're going to suppose that it's not, and we're going to draw OR and radii OT and OV. So basically I want to be saying that from this point out, this point out, and this point out, that those are going to be radii for this circle. So here as we look at this thing, basically QR is perpendicular bisector of TV. So as this thing comes up through, then R must be the midpoint. So basically we're saying that these two are congruent, and we also have OT and OV are congruent as well. So again, this is my heretic picture here, but I'm going to say, okay, well, if this is the case, that those two are going to be congruent, so now we're right here because all radii are the same, then I can say that OR is OR by identity. So whatever the distance is to OR is just going to be itself. And now it looks like I have two congruent triangles in theory, right? Even though it looks obviously wrong, I would have two congruent triangles. So if these things were congruent by side, 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 then what am I able to say about them? I'm able to say that corresponding parts of those triangles are going to be congruent. So then, basically it follows that OR and TV are perpendicular because these line segments form congruent adjacent angles. Again, the thing about being congruent adjacent angles is if I said this thing is this thing, and they're sitting flat on a line like this, then it's just going to be 180 divided by 2. And so here's where we get our 90. So that's why they meet perpendicular. So then, OR is the perpendicular bisector of TV, but QR is also perpendicular bisector of TV, which basically means O must really lie on this RQ line. So we see that that's a contradiction, and therefore we say, okay, O must therefore also lie on this. Thus, the supposition must be false, aka the thing we just assumed to start, and so therefore it follows that O is the center on QR, and the perpendicular bisector of the chord is TV, or excuse me, of the chord TV. Looking at example 1 here, take a peek at this. So here we have a circle O, and then we've got a radius of length 5. Just draw that in here. We have OE perpendicular bisector, or excuse me, perpendicular to CD. So I'm going to draw in my right triangle, or excuse me, my right angle, and then I'm also told that OB is 3. So if this chunk is 3, this chunk is 5, and this is unknown, I'm going to call this X, and this looks like just a simple, straightforward right triangle problem. So I get X squared plus 3 squared equals 5 squared. If you identify it as one of our Pythagorean triples, that's great. If you just want to do it out one step at a time. We will get there regardless. And we're going to ignore the negative root because we're dealing with side lengths. So we'd say x is 4, and what x distance we're talking about here is CB. So we'd say CB is 4. And now in terms of like what other stuff we can say about this, we could do the same thing and apply it over here with OD, and we'd be able to say that CB is BD, so therefore B is the bisector. So here we get perpendicular bisector again. So we can extend this out, and we get the full length of CD is 8. Let's talk about circles that are tangent. So we've talked about lines that are tangent to a circle, but two circles can be tangent themselves. So this circle here, and whoa, what a circle that is. This circle here are not tangent, okay? There's no point that touches between those two circles. I do have a line that comes through here and is tangent to the one circle, but it is not tangent to both. Here, I have this circle touching this circle at this point here. So here, we would say these two circles are tangent at one point. So here, for P and Q, we'd say these ones are internally tangent, whereas these ones are externally tangent. So O and R here meeting on the outside of these two circles, whereas this is on the inside. Now, definitionally speaking here, if my tangent point is between my centers of the circle, that's how I define it as being exterior. And if it's not, then it's going to be interior. So internally tangent versus externally tangent there. Guess I'll just write INT EXT. So I don't know if I was scrolled down far enough. Hopefully I was. But again, just for this definition, so you see the line of centers connects these two things. So from A to B here is my line of centers. So when I'm looking at this thing, that's going to help define whether I'm internally or externally tangent. So for two circles with different centers, the line of centers is just a line segment connecting the two of them. So it can be a line as well. So now let's talk about common tangent lines to circles. So these two circles, we said we're going to be internally tangent here, and we also have an externally tangent line. So here's my externally tangent line going through like this, and so again, it's just touching these circles at one point. So now here I have another example of externally tangent lines. Here I have tangent to the circles here and here, and then on the bottom, I have tangent to the circles here and here. Now here's my line of centers. So when I look at this center line here, it's saying, okay, if I went through that line, then I would be internally tangent, but this is externally tangent, and this is externally tangent. So what I mean by that is if I had a line that came through, let's pretend like we can use the line tool, right? If I had a line tool that came through like this and was tangent to both of these circles at one point, we would say that would be internally tangent, and we'll see that in 1 second here. So again, it is possible to have internal tangency between the two circles, again, intersecting that line of centers, but it just was highlighting the external ones first. And here we go to our internal. So here again, these two things tangent at this one point, and that line is going to intersect at that same point too. We would say this is internally tangent. And now here we have two tangent lines touching here and here. Likewise, we get here and here. So here, two examples of internal tangent lines. So one thing you guys should know how to do, a little hint here for you, is to draw circles or talk about circles in such a way that you can talk about the number of tangent lines. So if I want to talk about 0 tangent lines, and I'm talking about two circles, how can I draw them? I don't know. One way of doing it is just like that. Cool, there's 0 tangent lines there. If I want to talk about one tangent line, how can I do that? Well, one tangent line might look like this. again, we have these circles touching like this, and there's one externally tangent line there. Well, what if I wanted two tangent lines? If I wanted two tangent lines, I'm going to get a little tricky here. I'm going to have two overlapping circles, so there's like center, center there. And as I look at this thing, I have one tangent line across the top external like that, and I have one tangent line external on the bottom like that. Pretty sneaky. What if I wanted three tangent lines? If I wanted three tangent lines, I'm probably going to look something like this, where I've got one tangent across the top, one tangent across the bottom, and one tangent in between where those two circles are intersecting. So center, center on the circle. I didn't put centers on these ones, but there we go. We can even say these are concentric. Now, what if I wanted four? I've reached my final form of tangency. I get two circles separated like this, internal tangent, external tangent, and external tangent. So now here we see we have two internal and two external. Here we have tangent segments to a circle form external point are congruent. So this is a fairly straightforward proof, but as we look at this thing, we're just saying, okay, I want to prove that AB and AC are the same. And we're just saying that each of them are tangent. So basically we're going to connect this with BC. So we're calling BC a little bit of augmented line segment here just to connect between 2 points. So we can always do that. So now when we look at this thing, we're saying the angle for B is going to be 1/2 this BC arc. So this angle here is 1/2 that arc measurement. Likewise, I want to talk about angle C, and that's going to be 1/2 of the same arc measurement. So what does that mean about those two angles? It means those two angles are congruent. So now I've got angle B and angle C are the same. If angle B and angle C are the same, and we're looking at a triangle like this, then I know that these line segments are the same. This is an isosceles triangle. I mean, it's possible it's equilateral, but we just want to assume that it's isosceles for now. We wouldn't be able to conclude that without knowing this angle here. So now we look at actually applying this thing. So basically we get a couple pulleys of different lengths, and we're trying to explain why the straight pieces A, B, and CD are the same. Why are they equal? So when we're looking at this thing, I would say we probably want to think about it as I have a big red triangle like this, and then I have a small green triangle like this. So when we're looking at these things, we've talked a lot before about, okay, if I have two similar triangles, then the proportions are going to be the same, and so I'd get congruency here if these two line segments were the same. So as I look at this thing, basically we have the first one centered at O, and this one is using AB and CD to reach this next pulley centered at P. So basically, E is external to both of them, and so we know that EB is equal to ED, which is this part up top here. So I'm going to mark this just one tick in green. And so if I know that to be true, I know these angles are the same, and I know some other stuff about it. So basically, again, our external point, just based off what we just did, is going to be establishing these two segments are congruent. Now, if I look at this thing, I said, okay, well, what if I was dealing with the red instead, and I completely ignored this little P circle? If I wanted to do it this way, and I was just talking about AE as a segment, and CE as a segment, I could say that this thing and that thing are congruent. Because again, just looking at the bigger triangle, I'm basically saying this thing doesn't exist. So if that's the case, then these two are congruent. Well, what am I able to say about this little chunk in between? This little chunk in between just comes from subtracting off the green thing that I know. So if I want to figure out how do I get this blue chunk right here, it's just red minus green. So if I do red minus green for each of these things, it should come out as equal. So again, just my property of subtraction here. So because we get those two things are equal and those two things are defined as A, B, and C, D, we can say the A, B, and C, D are equal segments. So you could do it by triangle similarity. It's pretty straightforward to do it this way as well, just using the thing that we just did. Alrighty, so here we get a little bit more in depth algebraically. So I'm going to cover the geometry idea first, and then we'll talk to the algebra. So the first thing is I'm talking about a circle. Here we have a triangle, which is circumscribed about the circle, or we could say we have a circle inscribed in the triangle. So both are fine ways of describing this picture. So here we have it talked about as being inscribed. We got AB is 9. So from here to here is 9. We have B to C is 8. And then A to C on the bottom here is 7. So we got this one in blue, this one's in red, and then we got AB in green. So when I'm looking at this thing, I want to think, okay, what do I know? Well, the segment from B to N and B to M is going to be the same. And I don't know what that is, but I know they're going to be congruent because here's my external point to two tangents on a circle. Again, C, 2 tangents, and A, 2 tangents. So now as I look at this thing, I know each of these elements are going to be the same. My XX, my YY, and my ZZ. And so now I look at combining them together. So now I look at saying, okay, well, Z plus Y gives me 8. So that's this one here. And I say, okay, well, I also know that my Z and X add up to give me 7. And then I also know that my X and Y add up to give me 9. So if I'm trying to solve these things now, we have to use elimination. And we should have seen solving 3 variable equations before, but let's just say that maybe we're a little foggy on it. What I have to do is I have to use, a new color. I have to use 2 equations to eliminate a variable that I'm going to then combine with one of my other equations. Now typically we use 2 of them to create a 2 variable equation, and then I use another 2 of them to create another 2 variable equation. It may be that I can cancel off in such a way that I only have to do it once here. So when I'm doing this thing, I want to try and combine red and green together to get rid of a variable. I'm going to get rid of y. So I'm going to get rid of y. So I have x plus y equal to 9. And I have, I'm just going to write a little space in here to leave space for my z. So x plus y plus, and I'm just going to leave a space or put 0z equals 9. And then I'll rewrite this. So I'm going to say 0x plus y plus z equals 8. So now I want to change these in such a way that the y's are going to cancel off. I'm just going to choose to multiply the bottom one by -1. So I'm going to hit this whole thing with a -1. So that's going to change it. So now I have x plus y equals 9. And now I have -y minus z equals -8. Now I'm going to add these 2 equations together. I see that my y's cancel off. I'm left with x minus z equals 1. So now that I know x minus z is 1, in this problem, I'm able to kind of skip one step and combine these 2 to solve for my variable. So again, I'm going to take these 2 equations now and add them up. If I had a y in here, I would just have to combine it with one of my other first 2 equations, or you could go first to third. So first to third or second to third, either way, you just got to involve the third one. Here it just ends up being a little nicer, so x plus z, and I got x minus z. So x plus z is 7. We said x minus z over here was 1. Add these things up, what do we get? 2x equals 8. And so I get my x value of 4. Once I get my x value of 4, I'm going to plug it in somewhere. I can plug it in the top one here. So if I plug this in to the top, I'm going to get a y value of 5. And then I could plug it in back here for my z value, and I get a z value of 3. So again, just taking our variable that we know and plugging it back in. Once I knew my y value, I could use that to solve for my z. It doesn't really matter what you do. So I get x is 4, y is 5, and z is 3, and I have solved for these values. So solving for the length is the x, y, and z values respectively. So like am, for example, is x, whatever bn or mb, whatever is y. So again, we've solved for each of these. Here's the clean version, just to show you. So looking at 6.3.5 here, now we start getting into the length relationships that I talked about in the beginning. So here, if two chords intersect within a circle, so it does not need to be the center of the circle, just anywhere inside the circle, the product of the lengths of the segments, aka the parts of one chord, is equal to the product of the lengths of the segments of the other chord. So again, I'm going to write out what we're trying to prove here, and I'm going to do it in colors. So RV, I'm going to say is red. And then let's use TV as, I don't know if I want to use 4. Yeah, I'll use 4 different colors. TV we'll say is orange. VS we'll do in green. And then VQ we'll do in blue. So when we're looking at this thing, we're going to draw two little just line segments connecting these chords again. So these are determined. We can always just connect line segments here. So I'm just connecting Q and S. I'm just connecting R and T. So now as I look at this thing, I want to talk about it. So here, the only thing we're told is they're intersecting. When I am looking at this thing, what information do I have? I know that angle 1 and angle 2 are going to be the same. So why do I know they are the same? Because they're vertical angles. What else do I know is going to be the same? So as I look at this thing, it may not be immediately apparent to you, but what can I do if I want to talk about angle R here? So if I want to talk about angle R, it's an inscribed angle, right? It's sitting on my circle here. Whoops. There we go. So inscribed angles are 1/2 of their intercepted arc. So angle R here is 1/2 the arc ST. So I'm just going to jot that down. So I'm going to just say angle R equals 1/2 the measure of arc ST. And now if I look at this point Q here, again, on the circle, where is its intercepted arc? Intercept is this arc ST. So I'm going to also write angle Q is equal to 1/2 the measure of arc ST. What have we just established? These two are congruent. So now I'm going to put a little double tick here and a double tick here. Now as I look at this thing, it looks like I have angle angle. Angle angle is going to establish my two similar triangles. Okay, so let's draw those two things out. Again, I like to be very straightforward with how I'm representing these things. I don't like twisting my head and trying to guess like where is what. So I'm just going to start out by naming this thing. So I'm just going to start with the one on the left. I'm just going to call it RTV. So from R to T to V, and I'm going to label the things that I know. Angle R, I said, was the two arcs. I guess I can use the same color that I did before, just to make it a little prettier. And so I'm going to also put the same markings over here. So when I name this thing, I'm going to use that same orientation just so it's that much easier for me. I know that angle V here, so from R to V to T, is my one arc. So I'm going to also put a one arc down here. So now when I want to label my other triangle, I'm going to go find that two arc. Here we said was point Q. And then I'm going to go to my one arc was point V, and then back around to S here. So what I'm basically saying is that I have triangle RTV is, oops, that was not a good squiggle. That's better. Similar to triangle QSV. So what is special about that? Well, the corresponding sides of similar triangles are proportional. So if I want to talk about the proportionality of their sides, I already have an idea of what sides I am interested in, and I'm going to highlight those colors here. So the thing that I would like, and so I don't really care about QS and RT so much, so I'm going to basically ignore this and ignore this here, but I want to mark everything else. So TV, I said again, was my orange segment here. I care about that, and that's going to relate to SV. SV we did in green. Okay, now I want to talk about RV, which we did in red, and then we have QV in blue. So if I want to set up a proportionality statement, I could set up a statement that looks like this. I could say I've got RV over VQ is equal to TV over VS. Again, there's multiple ways that we could set this up. If you want to flip both sides, you could. If you want to compare one to the other, you can do it that way as well. So I'm just going for RV in red here, TV in orange here. So I'm just going this to that, and I'm going this to that. So blue to green. Here we go. All right. So call it cross multiplication, call it means extreme, property, whichever you want to do. Really, we're just cross multiplying these things to get the relationship, which is that my RV times VS is equal to TV times VQ. So again, I'll go one last time, underline these colors. Here's the red thing. Here's my green thing. Here's my orange thing. Oh, I think I grabbed the wrong orange. We're very color oriented here. Very color oriented. And there's VQ. Is this the relationship that we set out to prove? Yeah, absolutely. So this thing has been shown to be true. Do a little loop-de-loop here. There we go. Now we can use that to solve for example 4. So example 4 starts telling us some length. So we're told that HP is 4. Cool. We're told that PJ is 5. Thanks. LP is 8. Okie dokie. And then PM is a mystery. So in terms of representing PM, I'm just going to call it X. I don't know what that thing is. So this whole relationship, the thing that I just got from above, just tells me if I do this chunk by this chunk, it's going to equal this chunk times this chunk. That's all it is. Over here I get 20 equals 8x. Divide both sides by 8. And I get my x value equal to 5 over 2. And I'm done. That easy. Looking at 6.1 here, we would say that we have a secant and another secant. So when we're looking at these things, basically we're saying it intersects at 2 points here, and we're intersecting at 2 points here, common to an external point A. So basically both these things are reaching out to A. What we're going to say is two secant segments drawn to a circle from an external point. The products of the lengths of each secant is, with its external segment are equal. So what that means is this short length times the long length is equal to short length times the long length. That's all that means. So I'm going to just underline these the same as I just did here. Here we did AT in a solid, the squiggle right here, AB, squiggle, RA, solid. So in terms of proving this thing, I'm going to leave that up to you guys, but I'll give you a hint, and these auxiliary lines are really helpful. So when we're drawing in these auxiliary lines, just connecting T to B, just connecting R to C, I want to think about what this triangle is. So I'm going to draw a triangle here for you. So from A to B to T is one triangle, which might be helpful. It'd be cool if I could draw it back to the actual same point, but you know, aspirations, right? The next one we'll do in green, and that's ACR. So those two triangles are going to be very helpful. And again, a good way of talking about angles is where they go out for their intercepted arc. So again, for intercepted arcs, we would get the same if they're going out to the same intercepted arc. So 1/2 of that arc, 1/2 of that arc. Just FYI for you. Next thing we're going to look at here is, do I even want to do this one? I kind of drew all over my picture. Let's just draw the picture again. So here's A, intersect, intersect. Here we have R, here we have B, here we have C, here we have T. Cool, we have our picture. Good as new. So looking at this thing here, we're going to fill in the length that we know. So the first one I'll talk about is AR. So AR is going to be the thing from here to here. So I'm not told specifically what AR is. Let's look at AB. AB is 14. So from here to here is 14. I'm looking at BR. BR, it tells me, is 5. Well, really, by telling me that this whole thing is 14, and by telling me that this chunk is 5, I have indirectly been told that this chunk is 9. So I'm able to figure that out from giving me this information. And I'm also told that TC is 5. So just that chunk there is 5. I'm trying to find AC and AT. So what I would like to do is figure out AT, and I would also like to figure out AC. So when I want to set this thing up, I'm going to be using an X value. It doesn't really matter where you throw the X, whether it's here or here, but there's a direct relationship between these two things, which is that whatever this full long one is, it's just the little chunk plus the little chunk here. So I'm going to call this one my X. Oops, let's do it in same color. So I'm just going to call this one my X. So if I want to talk about this whole length here, I'd be talking about the length as X plus 5. Again, I don't know what the value is, but I can still use it as a full length. So I have this property which says if I take the little chunk out here to the first intersection times the longer chunk out to here, I'm going to have that set equal to this thing and then times that thing. So I'm going to set this up as 9 times my 14. It's going to be equal to, now here I've got X times X plus 5. So as I look at this now, I just get 126 on the left. So this thing is, I can maybe use another color, we'll use green. I've already used green, we'll use brown. All right, so this ends up being 126, and this ends up being X squared plus 5X. So we should know how to solve a quadratic from here, but basically what I'm going to do is I'm going to take this and subtract it over. So I get X squared plus 5X minus 126. So now we can look at this thing and look at factoring it. And so now this, I'm going to shortcut the factoring in. All right, so let's factor this thing ourselves to be X plus 14 and X minus 9. That's better. Here I get a possible answer of X is negative 14 and another possible answer here of X is 9. Now x cannot be negative 14 because we cannot have negative side lengths, but it can be 9. So here I'd have 9, and here I have 9 plus 5, which gives me 14. So in terms of AT, I would say it's 9, and in terms of AC, I would say it's 14. So if you wanted to use x minus 5 and x as this whole chunk here, you could. Again, the setup is exactly the same. You're going to get the same results. Here we get idea of, okay, well, what if one of these things is secant and one of them is tangent? So we're basically setting up a triangle here. And just keep in mind, we know some stuff, so I won't give the whole thing away, but I will try and set you up for success. So if a tangent segment and a secant segment are drawn from a circle to an external point, the square of the length of the tangent equals the product, the length of the secant with this external segment. So what that means is this thing here, TV squared, is equal to this chunk TX times the big chunk. Oops, I did that in the wrong color. There's TX. And there's DW. So when I'm looking at this, a thing that would really be helpful in solving this is maybe what angles I'm going to be using. And maybe I get some hints from using an arc here, or maybe using an arc here. So basically these auxiliary lines are going to be really helpful, and the two triangles I want to be looking at are TVW, so I'm going to say the big one here, and then another really helpful triangle that I get, let's do it in indigo, will be TXV. So again, it uses this angle in green and it uses this angle in purple. That's my first hint. And the second hint would be look at what arcs these intersect at. Here we're now just using that, and that's the last thing for today. So as we look at this, we're going to say, okay, well, if it's giving me SV of 3, and it's giving me RV of 9, then it is indirectly telling me the length of the full thing. The length of the full thing here is 12. Can't trick us. We're trying to figure out ST. So to figure this out, we're going to just call this thing X. So I'm going to use my setup of x squared is equal to, and now here where I'm going to have my big one, which was 12, times my little one, which was 3. The biggest mistake that people make on these is they do 3 times 9. It's the short one minus the long one. It does not use this chord here. So looking at this here, I get x squared equals 36. I'm going to take my square root of both sides, and we should see that we're just going to keep the positive one, which is x value of 6. And we're good to go. You're welcome, Oprah. Enjoy.